Welcome to this explainer on the double slit experiment. Today we're diving headfirst into a cosmic thriller that's going to completely shatter your intuitive understanding of reality. Seriously, we are going to explore a phenomenon that started out as a simple little test of light and somehow evolved into the ultimate test of the universe's most deeply hidden rules.
You know, the legendary physicist Richard Feynman really wasn't exaggerating when he talked about this. This single, deceptively simple laboratory setup literally holds the deepest secrets of the universe. He actually believed that if you can just understand this one experiment, you can understand the absolute core puzzle of quantum mechanics. It is, without a doubt, the locked room mystery of physics.
And this journey, it spans over 2 centuries of baffling some of the most brilliant minds in history. It all begins way back in 1801 with the British polymath Thomas Young doing these early 19th century light tests. Then it moves right through the legendary intellectual brawls of Albert Einstein and Niels Bohr in the 1920s. And finally, it takes us all the way to some truly mind-bending atomic-level research happening right now at MIT in 2025.
Okay, so to understand the massive twist in this mystery, we first need to look at how things normally behave. Think of classical particles kind of like paintballs. If you fire them through a stencil with 2 slits, they just form 2 distinct bands on the wall behind it, right? Makes sense. But classical waves, like ripples in a pond, behave completely differently. When waves pass through 2 slits, the ripples overlap, crashing into each other to create this alternating pattern of strong and weak bands.
But here's what happened when Thomas Young shone light through 2 parallel slits in 1801. It didn't create a paintball stencil. Nope. Instead, the light on the wall formed a banded interference pattern of bright and dark stripes. This happens because the light waves overlap, amplifying each other in some spots and canceling each other out in others. At the time, this pretty much seemingly proved, once and for all, that light was a wave, not a particle.
Well, quantum physics flipped this entirely on its head in the 20th century. Scientists began to realize that light and matter actually come in discrete, quantized packets. So they asked a completely new question. What happens if we fire pieces of matter or bits of light through the slits just one single particle at a time, leaving enough time between them so they can't possibly interact with each other?
And scientists didn't just stop at light. They started firing progressively larger things through the slits. They started with photons, then they moved to electrons, then entire atoms. And incredibly, they've even lobbed giant, bulky molecules made of up to 2,000 atoms, weighing in at like 25,000 Daltons through the setup. Because these are physical objects, you'd completely expect them to behave like classical particles, right? Like our paintballs. You'd expect them to form 2 distinct bands on the screen.
Instead, the result was entirely reality-breaking. Even when fired one at a time, these individual particles slowly built up a wave-like interference pattern over time on the sensor screen. This right here is the heart of wave-particle duality. It's the bizarre reality that all matter and energy in the universe exhibits properties of both classical waves and classical particles, entirely depending on the scenario.
So wait a second. The crucial point is this. How can a single particle interact with itself if it's literally the only thing in the room? Well, quantum mechanics tells us that a single, unobserved particle actually exists in a state of superposition. Before it hits the screen, it isn't in one specific place. Instead, it acts as a spread-out wave of probabilities. This single wave passes through both slits at the exact same time, interacts with itself, and determines the probability of where the particle will eventually land.
Now, scientists are a lot like detectives investigating a locked room mystery. They were unsatisfied. They wanted to catch the particle in the act. I mean, if it's a discrete chunk of matter, it surely has to go through one slit or the other, right? So they decided to place detectors right at the slits to peek at the particle and see which path it actually takes.
And boom, here is the massive plot twist of the universe. The very moment the detector is turned on to measure the path, the interference pattern completely vanishes from the screen. The wave behavior just disappears. Instead, the particles just form clumps behind the slits, exactly as if they were tiny bullets or paintballs traveling through only one slit. Just by observing the path, the outcome of the experiment fundamentally changed.
Now, because the pattern shockingly changes when we look, a massive myth kind of exploded throughout pop culture. You probably heard this one. It's the idea that human consciousness itself magically alters the fabric of reality. People started claiming that simply having a human brain observe the universe causes the universe to behave differently, which led to all sorts of wild spiritual interpretations of quantum physics.
All right, we really need to be absolutely clear and bust this myth today. The universe is not changing just because a human brain looked at it. Consciousness does not collapse the wave. What collapses the wave is the physical act of measurement. Extracting information fundamentally alters the quantum system, whether a human is standing in the room or not.
See, measurement in quantum mechanics is not passive. To actually see an electron, you have to bounce something off it, like a photon of light. This requires a real, physical interaction. When that detector interacts with the spread-out wave function to extract that which-path information, it forces that probability wave to instantly collapse into a defined singular position.
And what's super interesting is that even when collapsed, it's not purely a classical particle. When the measurement forces the electron through one observed slit, the resulting pattern isn't a perfect paintball smudge. It actually leaves a faint single-slit interference pattern, which is caused by the wave interacting with the edges of the single slit. This brilliantly illustrates that the quantum wave function still governs the particle's behavior, even after it's been measured and forced onto one path.
Naturally, this staggering reality sparked one of the most legendary heavyweight debates in the history of science between Albert Einstein and Niels Bohr. Einstein was super skeptical. He believed you could sneakily measure the particle's path without destroying the wave. He even theoretically proposed a setup using perfectly calibrated springs on the slits to detect the tiny momentum shift of a passing photon. But Bohr fired back, arguing that Heisenberg's uncertainty principle means any measurement, no matter how delicate, strictly destroys the interference.
Well, fast forward to 2025, and MIT physicists finally put Einstein's specific thought experiment to the ultimate test. They stripped the double-slit experiment down to its absolute bare essentials. For the slits, they literally used two single atoms floating in a vacuum. And when they scattered light off these atoms to measure the path, the wave was destroyed. They definitively proved Bohr right and Einstein wrong.
Basically, as Vitaly Fedosiev from the MIT team explains, the springs don't matter at all. The MIT team demonstrated with unprecedented atomic precision that it's the quantum entanglement, interacting with the inherent fuzziness of the atoms, that automatically erases the wave-like properties. The very act of extracting information from the system is what strictly forces the universe to pick a definitive state. Okay, if you thought that was strange, buckle up, because the rabbit hole goes even deeper. Scientists later developed something called the quantum eraser experiment. They found that if you let a particle pass through the slits unobserved, but you detect which slit it went through after it has already hit the screen, the interference pattern still gets destroyed. It's almost as if the act of measuring in the present somehow rewrites the particle's behavior in the past. It's wild.
So, at the end of the day, this explainer leaves us staring right into the profound abyss of quantum mechanics. The double-slit experiment continues to be one of the strongest demonstrations of just how bizarre our universe really is. It forces us to ask a deeply unsettling question. Does the physical world as we know it only truly take shape when things interact with each other? Think about that next time you look at a beam of light. Thanks for joining me, and keep questioning reality.